Also X of t. So X of t and H of t. The pitch would be where X of t comes from. You know how quickly this signal is changing, right? That'll be pitch. That'll be the frequency, right? That'll be related to the frequency, so how often this changes. And then also H of t changes. So for a man's voice, my H of t is, and for all of us really, we all have our own unique H of t's and our own unique X of t's. So by just changing those, we can change from a female voice to a male voice with a southern accent. We can do all of those things. Any questions?
So with that model, like you're looking, if you get the differential equation for that, that's H of t.
Yeah, that would be your H of t.
Okay.
And then so there would be some force. So this would be my H of t, however I modeled that, right? And then I would apply some type of a force. Right? You press it or pull it out and then let it go, and it would spring back and forth. So the force would be my X of t's.
Got it. So you've already given us H of t though.
Yeah.
Okay. Cool.
But you can do your own X of t. You can type in a second order differential equation for a vowel production and get a transfer function as easy as I did. That's all I did. Just type that into Google and it gave me that H of t. Hopefully you get a better appreciation of differential equations and why I'm so happy that we can solve them. So let's see, for today's class there's more homework. So it's on the note page, and then also I put that Excel sheet out with the homework listed, try to keep it a little more organized. I still don't know how to do the grading in terms of posting the grades. In that mentor system, it's just too laborious to do that. Or I'm too lazy to do it. So my threshold, so on the homework, what you're getting is 10 points a pop. Basically, if you turn it in, this is where I'll be the lenient grader. You turn it in, you get 9.99 points. Right, you turn it in with some effort. And then you hit the 0.001 point for deviating from sky, and you get your 10 points. So the threshold is pretty low. So the reason for that is that sometimes when I always hate to kill my problems as an undergraduate because I thought it always limited the time I could really learn because I had to do this busy work. So if you find yourself in that situation, you're working on a problem and I'd really like to study this a little bit more, and you end up spending an hour on that project, that one, and then you're like, oh shoot, now I'm in trouble. Don't worry about it. If you're not in trouble, just turn it in and just say, put it out there. Say, I really spent a lot of time on this project or this problem. That's okay. All right. But then there's probably not much encouragement to do the homework. So that's why I get in this terrible thing with homework problems that I got trouble with. So I'll get over it. But don't make it an impediment to your learning. So we were talking about Fourier transform. defined. Fourier transform is just x of t times e to the minus j omega t dt. Let's see, we talked about how close this is to the Fourier. X of s is the interval from minus infinity to infinity. X of t e to the minus st t, where s is sigma plus j omega, right? So the S domain was a two-dimensional space where it's sigma on one axis, j omega on the other axis. So this is my S plane. And it turns out control people and things like that like to work in the S domain, the S plane, because it tells you about stability of the system. For every other electrical engineer besides somebody that controls, we're mostly interested in just the j omega axis. And that is the Fourier transform. So, I can put in sigma plus j omega into the transform, the Laplace transform. And then if I set sigma equal to 0, that just gives me the j omega axis. And that gives me x of t times e to the minus j omega t, which is the Fourier transform. So basically, I've gone from a two-dimensional space to just a one-dimensional space, the j omega axis. Some useful functions. So there's some functions that we use repetitively when doing Fourier analysis. One is the rectangular function. Remember, one of the nice things about the Fourier transform is the signal doesn't have to be periodic. The Fourier series, I had to have a periodic signal. For a transform, I don't. So mathematically, I can write that as the 0, the magnitude of t is greater than 1/2. So anything beyond 1/2, the function is 0, and it's equal to 1, the magnitude of t less than 1/2. And then your author adds that it's equal to 1/2, or the magnitude of t equal to 1/2. So basically, there's a point. To be honest, we've never used this. I was thinking it's either 1 or 0. Mathematically, to be correct, it's equal to 1/2 at, right at t equal 1/2.